All right, welcome everyone to the Quebec Math Sciences Colloquium. Today in an unusual location and time, but with a great speaker. Our speaker today is Su Gao, who is coming from Nankai University, where he's a university chair professor. Su worked at University of North Texas for many years before moving to China. Back to China, where he was a Regents professor, chair, and the founding dean of College of Science. In his math achievements, he made several breakthrough achievements solving problems in descriptive set theory. And his most celebrated result is a theorem that all abelian groups induce hyperfinite actions. This is a joint result with Jackson. He is currently an editorial board member of the Chinese Encyclopedia of Math, Science China Math Journal, many logic journals and series. He's a council member of the ASL, and he currently has an uncountable number of graduate students at Nankai University. And he will talk about extremely amenable automorphism groups of countable structures.
Thank you very much. First, I'd like to thank Martin for this invitation. It's a great opportunity for me to be here and to meet the group over here. Also, Bo actually came from Nankai University, and when I first arrived in Nankai, he was in his last year there, undergrad. So we heard about the research strengths of this group already for a long time, and finally, I'm really pleased to have an opportunity to visit. And I appreciate that you actually changed the time and the place for your usual colloquium to accommodate my talk. So thank you very much. So today I'd like to give a report of some results about this topic. Over here, this is, first of all, I want to mention that this is joint work with my postdoc, Mahmood Etedadialiabadi. It's an achievement to actually pronounce his name. And the Feng is my graduate student now. And so I guess I'll just go ahead and explain the terminology and also give a little bit of history about this topic. So extreme amenability is a property about a topological group, which is really remarkable. And this basically said a topological group is extremely amenable if for any continuous action of this group on a compact space, it has a fixed point. So there's a point so that every group element will fix this point. So this basically says that I don't have it in my slides, but for those of you who know the basics about the topological dynamics, and we know that for every topological group, there's a universal minimal flow. And this is saying that the universal minimal flow is a single point. And therefore, the terminology amenable, of course, comes from the fact that on that universal minimal flow, there is a measure, which is a trivial measure here. So this, of course, is a remarkable property. It's actually being proposed. So the study of it started in the 60s, in fact, so first with semigroups. And then in 1970, Mitchell published this paper, and you can see that he talks about topological semigroup action and fixed points. And he started the paper with this property saying that whenever this S acts on the compact Hausdorff space, where the map is jointly continuous, this action, then Y contains a common fixed point of S. So this is exactly the property that we're talking about. And over here, he talks about semigroup S, okay? So up to even this point, the people's focus was on semigroup actions. So in that paper, there's a footnote. This is the footnote. There's a footnote where he alluded a little bit to the situation of a group rather than semi-group. And he basically said that for the group situation, there are some results, and basically the results are of the kind to say that that property might not happen for any group. Like basically it says that this F1, remember, was the property that we have. He basically said that that no non-trivial discrete group satisfies this property, right? So no non-trivial discrete group, and then also there are some other results saying that a large class of topological groups that do not satisfy P1. This class includes, among others, all locally compact abelian groups, totally bounded groups, blah, blah, blah. So a large class cannot have this property. And so he went ahead and asked, we ask a slightly simpler form of the same question. Are there any such groups at all? So this was 1970, okay. We didn't know if there were such groups or not, okay. And also a few years later, Veach. Now, of course, this theorem is famous now, and but it sort of obviously it comes from the stream of results over here. Veach proved that there are no non-trivial locally compact topological groups without any other assumptions, because here this originally the assumption involved abelianness, and here there's no abelianness, just the locally compact topological groups. No such groups can be extremely amenable. So of course this is the property, and so in the early days, it's really a mystery of whether these groups exist or not. And of course, then later on, there are many examples which came along. And so here are some examples. The very first example was given by Hare and Christensen in 1975. This is also a famous classical result now, that they consider this kind of a group which is L0 mu R, where of course R is the additive group that we consider, and the mu is a pathological sum measure. This is the paper that they defined pathological sum measure, constructed one, and then proved that it has this the property, extreme amenability property. Of course, even stronger than that. But this was the first example of extreme amenable groups. And then after that, a lot more examples came along, and basically I put them into three groups of results. And the first group over here are sort of the kind that it's L or L0 of some space to a group, an abelian group mostly, like in this case. Like over here, Furstenberg and Wise and Glassner. Well, Furstenberg and Wise, they claimed the result, but they never published it, of course. And the first publication was Glassner's paper in 1998. So it's quite some time has passed. So they proved that the L lambda T, lambda is the usual Lebesgue measure on the unit interval, and the T is the circle, the torus, or one-dimensional torus group, and this group is extremely amenable. Okay. Yes.
There are some students who may not have very good background. Could you just say in 2 words what is L not and L?
Oh, L0. Okay, so this is actually the measurable functions from the space to R. So with the of course, with the measure, the convergence over here is a convergence in measure. So that is the group, because in fact the algebraic operation, like these are functions, right? And you add them just as you add the sort of coordinate wise, right? So because the second group over here is abelian, so you get an abelian group. Okay. Because the inverse is coming from the inverse over here, and the addition comes from the addition over here, and these are the functions, right? They form a group. Okay. So
and the second row?
And the second row is also the same. Is actually all the measurable functions just from the unit interval to T, And of course, the addition in T is mod 1, right? Basically, so that is how. And also the convergence in this group over here, to make it a topological group, the convergence of this group is convergence in measure. Like if you have, in fact, you can actually define a metric over here. And of course, then the identity over here is just the almost everywhere zero function. Okay, so in other words, two functions will agree if they agree almost everywhere, right? So there's a sort of an equivalence class that you mod out in order to make it a group. And so then 2008, Farah and Selesky continued this line of research, and they basically considered L0 mu G, where G is a compact solvable group, and mu is a so-called diffused submeasure. So basically, is a definition that is broader than the pathological submeasure, and but in other words, this is a genuinely larger group, largest class of groups than the previous two. So it's a generalization of the previous two. And as you can see here, that they actually considered compact solvable. Of course, maybe not that, but this is compact and abelian, right? And so this is at least a generalization of Furstenberg-Weiss and Glasner's result. And then Professor Sabok's result in 2012, he actually generalized this by taking away the compact. So you don't need the compact. And here is the solvable group, general solvable group, and mu is a diffuse submeasure. Okay. All right. So this is one class of results. And you can see that it takes a long time from one result to the next. But the study of extremely amenable groups actually have been continuous, like even early on. So let me talk about some other class of examples. And for example, even before the second result of the L0 kind, Gromov and Millman, this is a very famous result in 1983. So they proved that the unitary group of the infinite dimensional separable Hilbert space, which is a familiar group, okay, that unitary group is extremely amenable. So, and the method they use is so-called concentrational measure, which is also a very important technique, and also an important phenomenon they discovered, in fact. So, and then along that line of research, Pestov in 1998 proved this other operator group, which is the group of all order-preserving auto-homomorphisms of the unit interval. So if you have the unit interval, you have the homomorphism that sends 0 to 0 and the 1 to 1, and then therefore it sends everything in between in an increasing way. Okay, that group over there, of course, this is the operator group. So in other words, if you have two functions, the group multiplication of the two functions are the composition. So this is definitely not an abelian group anymore. Okay, and even if it talks about the unit interval, so H plus I is a extremely amenable group. Also, Pestov proved it in 1998, and then in that same paper, he proved that a related group, which is the automorphism group of the rational numbers with less than this, in other words, the rational numbers with less than is just characterized as the countable density in order without endpoints, right? So because as a structure, there's only one such thing. And then this is basically just the all automorphism groups of this structure, okay? So, so this is obviously very much related to this because they look very much alike, except that this underlying space is uncountable and this underlying space is countable, okay? But they are both sort of operator groups. And then 2002, Pestov proved this also a very interesting result, which is the isometry group of the so-called unitary Eurozone metric space. I don't know whether people are familiar with that space, but it's a universal separable complete metric space. Okay, so this is a separable complete metric space that has every other separable complete metric space embedded into it. So if you take a look at that metric space and take a look at its isometry group, and that is what we call the universal Polish group. So I will talk about this later. And the Pestel proved that that group is also extremely amenable. So by the way, so far we have talked about these groups, and the Veitch's results basically said that if your group is locally compact, no way for it to be extremely amenable. So extremely amenable is actually, we consider it a largeness property, right? So small, locally compact is a sort of a smallness property. And then, those small groups cannot be extremely amenable, and therefore only large groups can be. And so these groups are all sort of in some intuitive sense large, because particularly this one, this is like the universal Polish group, and therefore it is it has every other Polish group as a closed subgroup of it. So this group is very big. Okay. Yes.
Silly question. So in examples 2 and 3,
Mm-hmm.
are the interval and rational numbers, are they very special? Or you could imagine that if you could replace interval or Q by some sort of higher dimensional thing, or something else.
Well, I will talk about it. So in fact, that is a nice question that leads us to the third class of examples where all of them are actually some sort of automorphism groups of countable structures. So which is the theme of today. So oh yeah, so I may as well just mention that Giordano and Pestel in 2007, they considered the unit interval with the Lebesgue measure. This is the standard Lebesgue space over here, and you consider the measure preserving automorphism of it. We still denote it as odd, but these are really measure preserving automorphisms, and this group over here is in the same sense, like the group operations are compositions, and then the convergence is convergence in measure. Okay, and so this group over here, they proved that it is extremely amenable. So all of a sudden, not only a lot of groups have been proven to be extremely amenable, but also a lot of them are actually familiar groups in some sense, because we actually study them a lot. Okay, and which is nice, but so far, if you count, we have seen 10 examples over here, sort of 9, 10 examples over here, and some of them are classes of examples. Like if you have a pathological submeasure and the L0 mu R is extremely amenable, so I'll talk about it later on. That the questions that I am interested in today is, like, are there infinitely many such things? Right. So because like over here, I have 5 examples on the board over here. These are generally just 5 of them. Okay. So these are not classes of examples. Okay.
If you think of the circle as a boundary of the hyperbolic space, you don't get any. Then of course you can put a bunch of like visibility measures, Patterson-Sullivan, whatever.
Sure, you can actually create probably more examples that way. But then our main question that we are interested in is, can you tell them apart? Are these really different groups? Yeah, so this is like, so now we move to the third class of groups, which I need to explain a little bit, which is automorphism groups of countable structures. And over here, the absolute master theorem is that proven by Kekris, Pestel, and Todorcevich in 2005, which basically they give a criteria for a countable automorphism group of a countable structure to be extremely amenable. So it's a class of groups over here. So let me state this, and I will define the terms later. Okay. But basically, you can get a sense of why we're talking about a whole class of groups. So first, we need to work with the notion of a Facet class of finite structures. You know this, then you know that. If you don't know it, then I'll define it in the next slide. So this is a bunch of finite structures, and then they have a limit, which I call the UK is the Facet limit of this class. Okay, this UK is generally a countable structure. Okay, and which serves as a limit of a whole bunch of finite structures, and then the KPT correspondence, as we say it now, says that the following are equivalent. This automorphism group of this countable structure is extremely amenable if and only if, okay, that this class, Facet class of finite structures has the so-called Ramsey property. I will define it, and then each element of K is rigid. So there are a lot of terms over here, okay, but let me just go ahead and define them. So these are 1, 2, 3, 4, at least the terminology that I need to define. And the easiest one is, what is rigid? Rigid means that the automorphism group is trivial, okay? So every element of K has a trivial automorphism group. So in other words, the only automorphism it has is the identity, okay? So that's rigidity. And then let's say define what is a Facet class. A Facet class is a class of, for me, there are different definitions, but a Facet class is a class of finite structures, okay, a whole bunch of finite structures, and it satisfies several properties. So first is isomorphism invariant. So if one finite structure belongs to the class and you have an isomorphic one, then that is also in the class. Okay, so we don't differentiate isomorphic ones. And then there's the so-called hereditary property, HP, which says that if you have a structure in the class A, and you have an embedding of another structure into it, you can view this B as a substructure because there's embedding of from B into A. Then this substructure is also in the class. Okay, so that's why it's called a hereditary property. You have a bigger structure in there, finite, and then you have a finite substructure. Then that finite substructure is also part of the class. And then joint embedding property, JEP, is maybe I can put it over here, that if I have A and the B, which are elements of K, then I can actually find a third structure C, also finite, which is in K. So this is called a joint embedding property. And the last one is the most important one, is called amalgamation property. The amalgamation property looks like the joint embedding property, but it's stronger, which is to say that I have A, and I have B, and I have C. These are all given. So basically, you can view this as I have a structure B and a C and a common substructure A. Okay, then the amalgamation property says that you can find a structure D, which is still finite. Okay, so that the B and the C jointly embed into D, but in addition to that situation, this substructure A over here, go in there, sit in, this entire diagram over here commutes. So in other words, A has only one copy in D, okay? So whether it's via B or via C, it goes into one copy over here. Whereas if you have, like in this case, if you jointly embed two structures in the C, and if it so happens that these two have a common substructure, it might be the case that that common substructure will go to different places. Okay. So these four properties define a so-called Facet class. So I'll give some more examples of this later on. And the Facet in 1954, he proved that if you have a Facet class, you're in a very good situation, because then you can form this thing so-called Facet limit, which is a unique countable structure, okay, that satisfies two properties. One is that it is so-called universal. In other words, every structure in K will be embeddable into that limit over there. And the second thing is so-called ultra-homogeneous, which is to say that if this common, let's say, structure has the property that if you have two finite substructures, which with a isomorphism in between, then you can extend that isomorphism to the entire structure. Okay, so that's the ultra-homogeneity, and these are very nice properties, and you can prove that if you have universality and ultra-homogeneity, then your structure is uniquely determined. Okay, so okay. So what are some examples of facet classes? Well, of course, the class of all finite sets is a facet class. So, you know, joint embedding property, this amalgamation property, no problem. It's just you have common set, right? Intersection, and you find a bigger set that incorporates all of it, no problem. Okay, but there are some more, a lot more. Oh, by the way, the facet limit in this case is just a countable set. That's it. Okay. I represented as using the natural numbers, but here is the interesting one, that the class of all finite linear orders also is a facet class. So in other words, if you have imagine there's a finite set with the order on it, finite set with the order on it, then you can actually find a third one with the order on it that incorporates both of this information in there. Okay, and also that. And so this one, the facet limit, is exactly the countable dense linear order without endpoints. Okay, and for example, the class of all finite graphs is a facet class, and the facet limit over here is the so-called random graph or the Rado graph, depending on who you ask, like whether it's graph theory people or descriptive set theory people. And here's another class, which is the class of all Kn-free finite graphs. So of course you vary n by n being 3, 4, 5, etc. Okay, so Kn means the complete n graph. So a K3 free finite graph is a triangle free finite graph, and these the facet limit over here are called Hansen graphs, Hn. Okay,
and this as an actual subgraph, not as a minor. Like it's not you know, like Kratowski or Robertson as a subgraph.
As an induced
just
subgraph.
Forbidden subgraphs, not forbidden minors, right?
Right. As a forbidden subgraph, yes. Okay, so here the class of all, here's another one, the class of all finite metric spaces with rational distances. Well, this was singled out as a facet class because basically Eurozone in 1927, which is almost 100 years now, proved that that there is a rational Eurozone space. That there's these are Eurozone space. These are facet classes. It's even, of course, Eurozone proved it even before facet defined these notions. But Eurozone basically worked with the same concept. Okay. And then the limit over here is called, nowadays called the rational Eurozone space. Okay, and that's exactly what the Eurozone did. And we can actually try to generalize this by here we consider only rational distances, but we could actually generalize it by considering a set delta over here for the distance values. So here a delta. Which is a subset of positive reals. I really should put here positive reals. It doesn't include 0. Is a distance value set if, you know, basically it is almost just a semi-group. Okay, so basically I would like to say that for every A, B in delta, A plus B is also in delta, except that sometimes the delta could be bounded. And in that case, I stipulate that the supremum of delta, which is the largest element of delta, is actually part of delta. And then, so basically, if you have a semi-group over here, like, you know, think of generators, and they generate a semi-group, and if you would like to cut off somewhere, just cut off somewhere, but make sure you cut off at a point which is included in the set. Okay, so this is what we call the distance value set. So rational numbers definitely is a different distance value set, but there are many others. Okay, so if you have, let's think about this. So if you have a distance value set which has only one element, okay, is one, then that is the first case. Okay, if it has two elements like a 1 and a 2, then it's actually the second case, not the second, but the graphs basically, right? So anyway, this is a situation that allow us to actually consider a class of things. And finally, just as a curiosity, the facility limit over here, we call it the delta metric Eurozone space. Okay, and denoted by use of delta. And finally, as a curiosity, I just want to note that the class of all finite groups form a facet class. So over there, these are easy to see. Like if you have A and then you have B, you want to incorporate into C, you just take the product. And this is not easy. This is not easy. So if you have a situation like that, you want to find a finite group that incorporates this. This is actually very non-trivial. And but it is a facet class, and its facet limit is the so-called Hall's universal locally finite. Anyway, this was discovered by Hall around 1959. Okay, so anyway, there are lots of examples of facet classes, but let's take a look at them. Oh yeah.
The edit distance somehow it doesn't appear in the examples.
Oh, the p-adic distance. Well,
it's sort of, it takes rational values, so.
Well, they are. I mean, so we could also consider. I didn't consider it over here, but we could also consider instead of metric spaces, ultrametric spaces, and with prescribed distance value sets. We restricted our distance values to countable sets because we want our classes, to be countable. Like basically, there are countably many finite structures, and then we want to construct a countable limit. So that's the reason why. So yeah, there are many more examples which I'm admitting over here. Once we have a countable structure, we equip this automorphism group with the pointwise convergence topology, just as we did before, and this will become a Polish group. Of course, you know me. We in descriptive set theory, we think Polish group is the best kind of object, right? If it's Polish, we're happy. If it's not Polish, we're not that happy. But anyway, so but not only that, but also these automorphism groups of countable structures, they also are isomorphic to closed subgroups of the so-called S infinity, the permutation group. Okay, so there's a characterization by Becker-Kekris which says that basically if you have a topological group, then being isomorphic to a closed subgroup of S infinity is actually the same thing as this group being the at least isomorphic to an automorphism group of a countable structure. Okay, and also there's a notion known as a non-Archimedean. So this also can be characterized as G as a non-Archimedean polar. So all of these are equivalent. Okay, so now coming back to take a look at all of these automorphism groups. So we find some familiar objects over there. Okay, and so these are just the examples I just mentioned, and I want to just highlight two related groups. And one is the H plus I that we talked about. The Pestel proved that this is extremely amenable. It is actually related to automorphism of Q less than, because this is a dense subgroup in here. Okay, and but notice that both of these are torsion free. Okay, because you cannot go back to the same point if you have a homeomorphism. Okay, and the isometry group of U, we also saw that the Pestel proved that this is extremely amenable. It is actually related to the automorphism group of this QU, this rational Eurozone space, because the automorphism group of QU is also dense over here as a subgroup. Okay. All right, but these groups, we now know that this is extremely amenable. What about these other groups? Okay, and the thing is that the Kekris-Pestov-Todorshevitz theorem will allow us to actually say, oh, look at these facet classes, look at, do they have the so-called Ramsey property? And is it the case that every element of this class is rigid? Okay, so you look at these classes that we just considered, only one of them consists of rigid structures, like the class of finite linear orders. Like if you have a finite set with a linear order, of course it's rigid, because the first one would have to be sent to the first one, second one to the second one, etc. But none of these others consist of rigid structures. Okay, like if you have a graph, of course you can rotate it from time to time, and so that basically says that none of these others, the automorphism groups, are extremely amenable. Okay, they're not. Okay, but how do you make them extremely amenable? You make the structures rigid. Okay, so how do you do that? You put an order on every one of them. Like basically you have these structures, and now let's just add an order, linear order to it. And so that becomes rigid. Okay, and then once you add the orders, then all of these are still, let's say, classes. They still have, let's say, limits, and their automorphism groups of these facet limits are going to be extremely amenable, like if they have the Ramsey property. Okay, but it turns out that a lot of them do have the Ramsey property, and therefore, so what is the Ramsey property? Let me just go ahead and define it. The Ramsey property that we refer to, probably I don't know how many of you know the definition over here, but of course, the chances are that a lot of people do know the classical Ramsey theorem, which is about sets. Okay, so here the Ramsey property we're talking about are referring to structures rather than just the sets. Okay, so that's why sometimes it's called the structural Ramsey property. Okay, so what is the structural Ramsey property? So we talk about structures. These structures are all finite structures. Okay, so I have A and a B finite structures. Think about a linear order. Think about a graph with a linear order or something like that. Okay, and so we're going to use this notation B choose A as the set of all substructures of B, which is isomorphic to A. Like you go ahead and look at B over there, and you try to identify which substructure looks like A, okay, and collect all of them. So this is like B choose A, okay. It's sort of like 5 choose 3, the same thing, okay, and then we use this arrow notation, which is first used by Erdős. And so for a positive integer K and a structure ABC, this is, if you have never seen it, this is going to be a complicated concept, but it really, I promise you, is really just a kind of a analogous thing as the original Ramsey property. So what this says this. So for every this arrow notation says that so here is C is a big structure, B is an intermediate structure, A is the small structure. Okay, so basically C arrows B A super A sub K is this. So you look at this big structure C, and look at all of the substructures that are isomorphic to A. So C choose A. Okay, for all of these, you give it a coloring. Okay, this is a coloring by K colors. Okay, 1 through K. So this K specifies the coloring numbers. Okay, for any such coloring, there is a substructure of C which is isomorphic to B. Okay, so that if you look at this substructure B prime, which is isomorphic to B, and look at its substructure of that are isomorphic to A, the C coloring on these things is a constant. Like all of them are colored the same thing. So this is the structural Ramsey property. Okay, but it's a notation, sorry. And the structural Ramsey property says that this K has the Ramsey property if for every K, no matter how you, no matter which K you specify, for every A and a B in K in this class, that you can find a C so that this arrow property holds. Okay, so this is the structural Ramsey property. And if K has this property and every element of K is rigid, then the automorphism of that limit over there is extremely amenable. And this is if and only. Okay, so this is a fantastic theorem which allows us to actually all of a sudden get a lot of extremely amenable groups. And this is the third class of extremely amenable groups that I'm talking about over here. Okay, and so what about the Ramsey property? Like let's go over the list of structures that we considered before a few slides ago. And of course, if you have just talk about sets have the Ramsey property, which is the classical Ramsey theorem. Okay, and finally, in orders, they have the Ramsey property. That was exactly what Pastov noticed in 1998. It's not a very difficult thing, but he proved that, used that to prove that the automorphism group of Q less than is extremely amenable. And later on, the three authors noticed that this can be generalized greatly, and therefore they got their results. So then from that point on, there are a whole bunch of people working on Ramsey properties of finite, classes of finite structures. Okay, and the leading people are Nasrallah and Rödel, actually in 1977 through 1983, they proved that the classical finite order graphs have the Ramsey property, which is the third class that we considered over there. Okay, and why is it 1977, 1983? Because Nasrallah actually, I think, gave a proof in 1977, but it's faulty. It has a mistake in there, and it was corrected in a paper by both of them in 1983. So that's why, like, basically by 1983 is a solid there. And 1989, Nasrallah proved that the classes will K free finite order graphs has the Ramsey property. Okay. Now our list of extremely amenable groups are growing, as you can see, right? And then 2007, Nasrallah proved the classical finite ordered Q metric spaces. The metric spaces that takes value in rationals, okay? And the M metric space. If you take value in natural numbers, these are these have Ramsey properties. But then it is actually, so all of them will have, correspond to extremely amenable groups. So we just want to notice that the Nasrallah's proof, if you're very careful, then you can make it work for delta metric spaces. That the generalization, remember that you generalize the Q and the N to any delta, any distance value set. Okay, countable distance value set. It's not that obvious, but it is true and it can be done. Okay. All right. So I spent most of my talk giving you the background, and now the main question is to be isomorphic or not is actually what we care about. Okay, that is the question. To give you some example, Ouspensky proved that the homeomorphism group of the Hilbert cube is a universal polar in 1986, and then in 1990 he proved that the isometry of U is a universal polar group as well. Okay, so are these groups topologically isomorphic? So one way to tell could be that the Pastov proved that the isometry group of U is extremely amenable, that we know that, and then when you think about the homeomorphism group of the Hilbert cube, obviously it has an action on the Hilbert cube without a fixed point. So this is not extremely amenable, and therefore they cannot be topologically isomorphic. But what about the homeomorphism class of I? It's the auto-homomorphisms that are increasing. We noticed before that this is torsion-free. Okay, so none of these other groups are torsion-free, and so even if this is extremely amenable, it is not going to be isomorphic to the other two. Okay, but this is too tedious. Like you take two groups and say, are they the same? Take two groups, are they the same? So what we want to consider is just that we have a list of extremely amenable groups over there, but look closer, and are there infinitely many pairwise or non-isomorphic ones in there? Okay, so that was the question. Okay, that's sort of the motivating question for our study over here. So if you actually look closer at Pestov in 1998, he already proved that for any infinite cardinal kappa, there is an extremely amenable topological group of weight kappa. Okay, so of course, when kappa is big, or these groups are big, it has nothing to do with sort of the groups that we are familiar with. In fact, every one of them is of the form automorphism of some kind of dense linear order. Okay, it's just a very big, very long order, etc. Okay, so but other than kappa being equal to omega, none of these groups are separable or second order or Polish or anything. And there's only one Polish group, which is the automorphism group of Q. All right, so our result I want to report is that we proved that there are continuum many such things, and continuum many pairwise non-isomorphic extremely amenable groups, which are separable metrizable. Unfortunately, the first class we were able to consider was separable metrizable groups, but they're not Polish. Okay, and we will see in a moment. And the second, then we work harder and we get Polish groups. Okay, so we get a continuum class, size class of pairwise non-isomorphic groups that are Polish. Okay, so let me tell you a little bit about what are these groups that we're considering. So the groups that we're considering is we start with this countable distance value set. Okay, I told you that for every one of them. Okay, for every one of them, now we consider instead of U sub delta is a countable structure, and we used to consider the automorphism group of it as a countable structure. But here I want to consider the isometry groups where the topology on this is with respect to the topology that is induced by the metric. So you have an underlying space that has a metric on it. So you consider the isometry groups that obviously, with respect to that metric. Okay, so that isometry group, unfortunately, this is what's making it a separable metrizable but not Polish. Okay, because in order to make it Polish, you need to take the metric completion of the underlying space, and once you make the metric completion, then things are different. So so we have the following theorem. First of all, every one of them is separable metrizable, and the second is that it is Polish only when this delta set has a positive lower bound, like over there, like the inf of it is really positive. Okay, you think about these metrics, like for example, Q doesn't satisfy this property. Okay, so it's only Polish if that is the case, and we prove that it is only extremely amenable if it's the other case. It's extremely amenable only when this delta has inf 0. It's Polish only when the inf delta is not 0. So that's why these are never Polish. Okay, they are separable metrizable but never Polish. Anyway, so and in fact, if you think about that, the deltas that are not bounded, then all of them, when you take the completion of the underlying space, they give you the isometry group of U. So in other words, these groups that we consider, they all have, when you take the completion and etc. So they're all dense in the isometry in one group. Of course, we know that if you know a little bit about Polish group, is that you have a subgroup of a Polish group which is Polish, then it must be closed. So it cannot be dense in there and being different. Anyway, so this is the class that we consider, and we do. However, we are able to tell them apart. That's sort of the important part, which is the following thing, that consider this class of groups, right? So what we vary is delta and the lambda. These are countable distance value sets. And remember, when are they extremely amenable? It's when if delta is 0 and if lambda is 0. Okay, so those are the situations when they're extremely amenable. Okay, but in those situations, they are isomorphic as topological groups exactly when they are isomorphic as abstract groups, very strong. And then if and only we can characterize that by this following notion, which is a equivalence notion between the two sets. Okay, the delta and the lambda, we call it equivalent, but so what is the equivalence notion is that there is a bijection between delta and the lambda, these distance values, okay? There's a bijection so that for any triangle, D1, D2, D3, for any triple over here, sorry, yeah. For any triple over here in delta, it forms a delta triangle. What is a delta triangle? Is that you say, here's D1, here's D2, here's D3, then it satisfies the necessary triangle inequality. Very easy. Like two things added will be bigger than the third. Okay. So this is a delta triangle if and only if when you use theta to send it to the other set, to send it to lambda set, it is a lambda triangle. Okay. So this is a notion of delta and the lambda being equivalent. Okay. So yeah, so by the way, I actually use this double total over here to denote their equivalence. Okay. So in other words, we did figure out like when they are topologically isomorphic or not, as a group, as a topological. Okay. Okay. So okay. Just one word on this because I'm short on time. But so how do we prove that? We actually use a result that went back a few years ago. This was proved. This looks very similar, but it's proved by a different set of authors, Etedadialiabadi and myself and Lemaitre and Mallory. So in 2021, we actually considered these really automorphism groups. Remember, these are countable structures, and we consider automorphism groups instead of the isometry groups with the metric topology. These are looking at them as countable structures. Okay, so in that point of view, we also proved a similar theorem, which is that the automorphism groups, their automorphism groups as topological groups are isomorphic or is equivalent when they're isomorphic as abstract groups. And I'm going to jump directly to here. If and only if delta and the lambda are equivalent in that exact same sense. So we proved this result using this, but I'm not going to go into details. Okay. Why are there uncountably many different ones? So let me give you an example. Like basically, if you work with any possibly irrational numbers and consider this set, which is, I call it delta sub alpha, which is all the P alpha plus Q where PQ are rationals, and only consider the positive part of this. Okay, so these two sets, such sets are distance value sets because you take two values, you add them, and there's still such a value. So and they're unbounded, so I don't have to worry about the bounds. Okay, and two such sets are equivalent in that sense we just defined, if and only if that delta alpha and delta beta as sets are related by one positive real number. Okay, you just find one positive real number, multiply on it, you get the other one. So it's just a scaling of the set. But this is also if and only if you can find ABCD rational numbers so that the beta is equal to A alpha plus B over C alpha plus D. Okay, so this is actually, I'm gonna later on formulate this as GL2Q action on the reals, right? And this is actually exactly that equivalence relation on the irrationals. Okay. Oh yeah, by the way, I think this is exactly why we gives us that there are uncountably many of them, because obviously there are uncountably many different alphas and betas that are giving us or if you look at this is even more clear, because the equivalence class the equivalence class of such a thing is actually countable. Like every equivalence class is countable. So obviously there are uncountably many inequivalent such things, and they correspond to non-isomorphic extremely amenable groups. So what about the Polish ones? And these are separable, completely metrizable, but not separable, metrizable, but not Polish. Okay. So what about Polish ones? The Polish ones we have to work with, remember those orders, for the Polish ones, we actually look at the facet classes with the orders. The KPT, did tell us that the automorphism group, this time is really the automorphism group, that they are extremely amenable, like for any countable distance value set, except that we now need to prove sort of the same theorem about when they are isomorphic or not as a topological group. So here, this is actually, luckily we got the same result, which is that these things are isomorphic as topological groups if and only once again, delta and the lambda are equivalent. So that's why you got uncountably many also. Okay. So I guess in the last couple of minutes, I would like to just make some remarks over here, like some ingredients of the proof. So one ingredient of the proof is a theorem of Slutsky, which is a curious thing, which is like if you work with a countable distance value set and A, B be two finite subsets of the Eurozone space, then he proved this very nice result, which says that the automorphisms of U delta, which fixes A pointwise, and the automorphism of U delta that fixes B pointwise, these are all subgroups. When you take the subgroup generated by this is dense in that subgroup. Okay, over there. And so in our proof, we need to actually prove a ordered version of this, which turns out to be a little harder because we have to work with some additional objects over here, but they turn out to be true. And another ingredient was that you probably noticed that in my final theorem, I didn't have the equivalence of two groups being isomorphic as abstract groups, right? So all of the previous ones says, yeah, if they're abstract group, but so the reason over there is that we are able to do the equivalence with the abstract group in the first case because Slutsky in 2007 proved this theorem, which is the automorphism group of U's of delta. Okay, really automorphism group has so-called ample generics. I'm not going to define what it is, but this ample generics will give us the automatic continuity. Okay, and which gives us like if they are continuous as abstract groups, then they're continuous. If and only if they are isomorphic as topological groups. However, if you put the order over there, okay, if you want to prove the abstract, the same thing, you would like to say, maybe this has ample generics, but it doesn't. Okay, so Slutsky proved that it does not have ample generics. That's the point of this paper that he wrote in 2012. This paper is called non-genericity, non-ample generic. So that was what he proved. So anyway, okay. Oh, I do have one slide, which is perfect. I do have one slide about descriptive set theoretical results, which is that if you consider now the class EA of all extremely amenable non-Archimedean Polish groups, okay? I'm not going to define these terms, but they form a nice class within the class of Polish groups. So they form a broad class over there. Okay, so this is once you form a broad class, you can ask all sorts of questions in the framework of the descriptive set theory. And then the question is, what about this isomorphism relation? We proved that there are uncountably many classes for that isomorphism relation, but we can prove something stronger, which is that, remember that we considered these GL2Q action on the real rationals, right? And we also considered this double total equivalence relation. You can code it using some kind of coding. And this is the isomorphism relation on EA. So all of these form a strictly increasing chain in the broad reducibility hierarchy. Once again, I'm not going to define broad reducibility, but basically the gist of it is that these equivalence relations are increasingly more complex. So E0 is something that we understand very well. Every one of them is more complex than the previous one. Okay, so but you know what this these results, our results say is that now you know that it's actually above E0, but exactly for those working in descriptive set theory, the real question is what is this complexity? Okay, to be exact, and we don't know. So because we don't know any the exact complexity of any of these equivalence relations, which is very strange because this one over here, we thought that somebody should know about it, but I haven't seen anything. Like this is the GL2Q action on the irrationals. Okay. If it's SL2Z action on it, it's hyperfinite. But for the GL2Q one, I haven't seen any results. So anyway, this is all I want to talk about. Thank you very much. Yes.
You said earlier that extremely amenable group tends to be large. But when you look at the property, we see that we have a condition that needs to satisfy for every element of the group. So I guess that means that when we say that extremely amenable groups are large, what we are really seeing is that they don't really act on many topological space. So is it possible to say something like, oh, the topological space where I have some faithful function out like this?
Well, yeah. So yeah, that's a very good question because really, I mean, when we say extremely amenable groups tend to be large, that really was motivated by the early result that the locally compact groups are not extremely amenable. And now we have a more sophisticated kind of idea about it. And basically, we know that not all large groups are extremely amenable. So that's exactly what this is telling us, is that of course there are all sorts of large groups over there, and but now at least in the realm of automorphism groups of countable structures, we now know that it's subtle, right? You know, it's not just that. It's not the case that you have an extremely amenable group and any larger group is extremely amenable. That's not the case. So yeah, I mean, so that's that part, and so I think that this every element is rigid part is actually exactly sort of hinting that when you have these properties, then you can actually consider the universal minimal flow. And then in that case, the universal minimal flow will actually stay small.
Is there a, like, in classical set theory, right? There's a notion of Ramsey number. And do you think there is, and then something like there is R of K or R of like AB? Are there some interesting visualizations in this?
I am sure that in the structural Ramsey property, this is a big war. Ramsey properties, even
Ramsey degree.
Right. Ramsey degrees, right. So there are actually people who study that, but yeah. So for example, there's something called a big Ramsey degree, right? Which is just I think there are two senses. One is in the traditional Ramsey theory, you want to say, okay, so how large you need to go in order to find these structures, like maybe this one, the amalgamation, right? So that that kind of computation is very combinatorial, has a lot to do with a lot of things, number theory, whatever. But there's another thing which is called the big Ramsey class, which is to say that if you're not able to find a single, there's an ABC thing, right? The ABC thing is like you find this B so that all the substructures are colored the same way. That's sort of like saying that you use number one to color it, but maybe there's a sense that you can find this B so that all substructures of B that is isomorphic to A are given at most two colors, like are colored by at most two things, or maybe at least at most three things, etc. That's another subject which has generated a lot of research, but difficult. I think they're very difficult. Like for example, Natasha Delbrinen's results. I think she proved like big Ramsey class degree to be 2 for this one thing, and that's a Annals of Mathematics or JMS article. Yeah, that's a very deep subject. I mean, Ramsey class, of course. Yes.
You mentioned the last slide, you have the observation on the amenable class.
Uh-huh.
You said that you don't know which complexity it fits exactly into. But are there any results that say that this computation is countable?
No. So I think these are all we know. So you can see that some of these are benchmark results, constellations. This last one was what we call the isomorphism countable structures, which is, obviously extremely amenable group automorphism is actually reducible to that, but we don't know how to characterize this. For example, is this one non-Borel? Like you have two countable distance value sets. You wonder about their equivalence. We don't even know that is that. It looks like a non-Borel analytic equivalence relation, but we don't know that it is non-Borel. The first three we know they're Borel, but we suspect that they're very low. Like there's a lot more to it. And also there is another angle to look at this. Like it's probably not doable using these delta metric spaces, but if you look at ultrametric spaces, if you look at delta ultrametric spaces with orders, we don't, they are extremely amenable. The automorphism groups are extremely amenable as well. We suspect that over there, if you can prove that two such things are topologically isomorphic, if and only if the underlying spaces are, the sets, the distance value sets are actually order isomorphic as a countable, set. If that is the case, then we know that we're putting it right here. So, however, that's very difficult, and we don't have any technique to do that.
So, for Mendelian groups, you can do harmonic analysis, right? Like
Mhm.
you can look at representation. So, one extremely amenable should be something nice and interesting, right?
Perhaps,
One,
yeah.
Right, and then
Yeah, it's hard to tell. I think
so I mean, certainly people people who have looked at representations of the symmetrical right things like that.
yeah, so in fact there's for example, if you look at the very first like Christensen, higher Christensen results, those groups that have that are called exotic, they don't have any non-trivial unitary representation. So So there are actually, so yeah, extremely amenable is actually one property that looks like very strong, very strong, but we have groups that are even stranger. But yeah, so I think all these notions are not very well studied. And I suspected that because Gromov and Millman, they proved the unitary group of Hilbert space is extremely amenable. But they use this concentration measure technique, and I don't know, maybe they will actually have some similar idea over there, trying to maybe that's the motivation. They try to do something that is sort of a harmonic analysis like on those things, and but this looks like an obstacle, right? This looks like well, you might not be able to do it. So, so for example, there's a notion of so-called Levy group, which is referring to exactly those groups that have the concentration measure phenomenon, which is stronger than extreme amenability. Not all extremely amenable groups are Levy, and Pestov, I think, was the only one who kept working on these things, and the group that was a number of them are Levy, a number of the other groups are Levy, and but in general, we have a much smaller collection of Levy groups, known results of examples of Levy groups than extremely amenable groups. So, for example, are there infinitely many? We don't know. Yes.
Are there any examples of groups which don't have any non-trivial action on the locally compact space of like further restrict? Is it on the same as extremely amenable, or are there any examples?
It'll be extremely amenable. I haven't seen the concept. I don't know. Yeah, but that's interesting.
Yeah, why need non-comedian in the first paper? Why need this? Apparently, automorphism works on
It's too okay. So this has to do with a program that is promoted by Kepler's Nies and Tent. So Kepler's Nies and Tent published a paper a few years ago. They argued that, of course, you can take a look at all Polish groups and look at the isomorphism as topological group isomorphism on that space. But it's not clear that it is actually going to be sigma 1. I think that it's actually more complex. But if you restrict your attention to our non-Archimedean, then they're manageable. Like they proved that a lot of these classes are overall. Roski compact and this and that, like a lot of concepts turn out to be Borel. They don't look like Borel at all. Like over here, extreme amenability, of course, they don't like Borel also, if you just look at the definition. But this is what making it possible to prove that it's Borel. Yes.
So how Borel?
How Borel it is?
Like, is it specific to the theorem, or is it just?
Let me think. Okay, so the proof is basically to use the Kekres-Pestov-Todorcevich correspondence. Because basically over there, what we use is that if you have any non-Archimedean group, it is going to be an automorphism group of an auto-homogeneous structure. And therefore, that itself is a facet limit. And then you go to, once you have a facet limit, you have a facet class by looking at the age. And then you can actually go out there and characterize the Ramsey property as well as the rigidity. So I think, yeah, if you unravel all these definitions, you see that it is Borel. But I think, it's not going to be over 10 quantifiers, right? But yeah, we were not very careful. It's not pi03 either. I think it's something like pi05, pi06.
Well, thanks again.